Hey, grade nines. Today we're going to be discussing topic 1.2 of Unit D, which is current electricity. Last time we discussed static electricity and how electrical charges can form in objects. And albeit very cool with things like lightning and Van de Graaff generators, static electricity is not a really good way for us to power objects because basically you get a buildup of a charge, then you release the charge all at once. What we need to do is we need to basically create a steady flow of charged particles in order to power things that we use day to day. And for that, we need to use what's called current electricity. So what we need to do, and when we discuss a current is simply a steady flow of charged particles that are moving through what we call a circuit. And I'll be getting to what makes up a circuit here in a couple of seconds. But in order to create that current, we need a couple of things. First, we need a power source. We need some kind of an energy source. And when you think about it, if you're using, let's say, your iPhone or your mobile device, that would be the battery. The battery is going to be your energy source. It's actually going to it's the source that creates the charged particles that are going to basically move through the circuit that are going to allow you to create that electrical current. The second thing we require is an actual circuit that is unbroken. You can't have any breaks in the path for the charged particles. If there's a break anywhere in the circuit, you're going to run into trouble. You may have heard of what's called a short circuit. Well, that's what a short circuit is, and we'll get to that later in the unit. But rest assured, you require a steady path or a continuous path for these charged particles to move through in order for you to actually create that current. Now, current itself is measured with units, just like we would measure distance with kilometers or weight with grams. And the amount of electrical current is measured in a unit called amps or amperes, which is abbreviated A. The unit is named after a famous scientist by the name of Andre Marie Ampere, who basically did some really cool stuff back in the 1700s. This guy was way ahead of his time. He was the guy who discovered that like charged particles, like we discussed last day, that a positive and a positive charged particle are going to repel one another. And if you had a negative and a negative, they would repel each other. And if you had a positive and a negative, they would attract one another. He was the guy that came up with that and understood that was happening. He was the first scientist to come up and discover that. As well, he was way ahead of, you remember back in Unit B, we talked about Mendeleev and the periodic table. Ampere he did some crazy stuff organizing elements before there was even a periodic table. So he was about 50 years ahead of Mendeleev in organizing and categorizing elements. Didn't quite create the periodic table, but did a lot of organization of elements before the periodic table actually had been invented about 50 years later. And finally, he actually theorized the existence of an electron. This is about 100 years before J.J. Thomson actually discovered the electron as part of his raisin bread or raisin bun model of the atom, which we discussed back in Unit B. So this guy, really was ahead of his time, and for this reason, we've named the units of current after him. Now, as far as an actual current goes, you're going to require something to have these charged particles move through. And we talked about this in Unit B as well. We talked about things that are called conductors. Conductors are substances that allow charged particles to move through them very easily. And you might remember that certain substances like metals are great conductors. Ionic compounds are great conductors provided they are dissolved in water. If they're in an aqueous solution, they are fantastic conductors as well. So it's for this reason when you think of electrical wires, when you think of the wiring in your house, they're usually they are made of metal because those are your best conductive substances. You need something that can actually allow these substances or these charged particles to move freely through the circuit in order to actually create the movement that we require to create the steady flow of charged particles that we require. Now, as far as the circuit itself goes, we require several things to make a proper circuit for this to actually happen. I've already mentioned to you earlier that we require an energy source, and here's my little battery that I've drawn. And you might know that there's a battery the batteries have a positive and a negative terminal, which we'll get to as we discuss batteries here in some upcoming lessons. But for now, just be aware that there is a positive and a negative terminal for a battery. There is my conductive wire or my conductive material or my conductor that is going to comprise the circuit. but I require two other things as well. So I've got my energy source and my conductor for my circuit, but I also require two more things. One of them is a load. Now, a load is pretty much what you are using the electricity to power. If it's a light bulb, that's going to convert electrical power or electrical energy into radiant or visible light energy. Also, some heat energy as well. If you have your iPhone, your iPod, you're listening to music. Basically, that's converting electrical energy into audio energy or like audio wavelength energy. So a load is simply anything that's on the circuit that's going to convert the electrical energy into another form of energy, and it's essentially what we're going to power. If I turn the lights on in my house, the lights are the load in that circuit when I turn them on. And speaking of that, that's the fourth thing I require in my circuit. I also require a switch. You understand that when you come into a house, you have to turn the lights on and off, right? So right here is my switch. Right now the switch is engaged. This means that my circuit is actually active right now. But if I flick the switch and I do this with my switch, now you'll notice that I do not have a complete circuit, which I told you earlier was a requirement for these charged particles to move through. If I break the circuit by opening it up with that switch, I basically do not have a flow of electrons, and basically I cannot power anything that's on that circuit. So in this case, in this configuration, the light would not be on. If I switch it back on, and I put my switch back into this configuration, now my light is actually going to be on again. But again, you understand what a switch is because you use light switches in your house, but that's exactly what you require as your fourth element for a circuit. So just to recap, you require an energy source, you require some form of a conductor to conduct the actual charged particles through the circuit. You require a load, which is going to convert the electrical energy of the charged particles into another form of energy. And then you'll finally require a switch, which will allow you to start and stop the flow of charged particles at any given time at will. So that's basically what you require for an actual electrical circuit. Now, before we finish up the topic of current of electricity, I'd like to discuss one more unit of electrical energy that we need to be aware of, and this unit is called, or this, I guess this is called voltage. Voltage is something that we're going to be discussing quite a bit in this unit as well. Now, voltage is different than current. Voltage is the difference between it's a difference in charge between 2 points in a circuit. So if I've got a substance that's really, really negative on one part of my circuit and one part that's really, really positive or maybe more close to neutral, the bigger the difference is between those two parts of the circuit, the higher the voltage is going to be. The faster the particles want to move because they have that attractive force that's drawing them from one end of the circuit to the other. So that's what voltage is. So if you think about voltage, and I use the analogy of water for current, voltage would not be the amount of water. It might be like take a waterfall. If you had a really high waterfall, a higher waterfall would have a higher voltage because you've got water that's falling further. It's able to move faster because gravity is accelerating it further as it's moving down the side of the cliff face. Voltage is pretty much the same thing. The bigger the difference in charge between 2 points on a circuit, the faster the charged particles want to move through that circuit. Now, just like amps, which we measure current with, volts are named after a famous scientist. They're named after a scientist by the name of Volta. He was an Italian scientist, and his big claim to fame was he invented the first electrical battery. This was back in the 1800s or the 1700s, 18th century, and that was most people think of batteries or maybe something that was invented in the 20th century, but no, they were invented way back in the 1700s by this Italian scientist by the name of Volta, and we now name volts. And by the way, the abbreviation for volts would be V, which we'll be using again later in the unit when we discuss units of electricity and how we calculate voltage and current, and again ohms. But yeah, we're looking at V for voltage. And we can measure voltage using a voltmeter. And this is used quite often. Let's say you have a battery. You want to check to see if a battery has, if it's dead or not. You can put one a part of that voltmeter on the positive end of the battery, you put the other end of the voltmeter on the negative end of the battery, and that creates a circuit that runs through the voltmeter, and then it will actually tell you the difference in the potential difference between both sides of the battery. If there is no potential difference, then the battery is dead. If the battery is a 1.5 volt battery and it's fully charged, it should roughly have 1.5 volts of potential difference between the two terminals of the battery. And as you use that battery, that voltage will drop lower and lower and lower until the battery cannot provide you any more energy to actually power the circuit. And then you either have to charge the battery again, or throw the battery out and put it into an eco station to get properly disposed of. So that's basically what voltage is, and that's pretty much the end of today's lesson on current electricity. For homework, here it is. You've got questions 2 and 3, 5 and 9 on page 283 of the textbook. We'll see you guys again next time for topic 1.3.